now that we've spent the first part of the year looking at some different functions and how we do calculus on them, it allows us to look at some more interesting questions with rates of change. You remember we looked at rates of change last year, but at the time all we knew how to differentiate were polynomials and things like that. So let's just recap this idea of rates of change. Difference, I suppose, between, say, a 2-unit, which I suppose we don't really need to worry about, and 3-unit is that in 3-unit, you might need several rates to come up with a solution, whereas 2-unit, they usually just play with one rate and go with it. So your chain rule, implicit differentiation, rates of change, whatever you want to call it, it's all the same idea, okay? So let's have a look at a classic one, a spherical balloon being deflated. Radius is decreasing at a constant rate of 10 millimetres per second. Calculate the rate of change of volume when the radius is at 100 metres. Because if you think of deflating a balloon, the volume doesn't come out at a nice constant rate. And all you got to do is think of the sound. Imagine the sound. See, it gets quicker at the end. So, let's see what we can come up with. We want to find dV dt. What information have we been given? We know dr dt is negative 10. So we want dV dt. We've got dr dt. If we can come up with a relationship between V and R, we can do some calculus on that, and we should be right. Well, yes, of course, we have a formula for volume of a sphere. So 4/3 pi r cubed, dV dr is 4 pi r squared. So subbing that all in, we get minus 40 pi r squared. So it's negative, so yes, it's decreasing, that all makes sense. We want to find when it's 100 millimetres. So that's a substitution question there. Whoa, look at that number, that's a big number. 400,000 pi. But the units on that would be millimetres cubed per second. Millimetres cubed per second. Okay, this time our bubble is expanding. And so we're blowing into the balloon. So this time the volume would increase at a constant rate, because usually when you blow in, you just go, and you blow a constant amount of air into the balloon, although this is a bubble, same thing really. Rate of increase of the surface area. Okay, so we want to find ds to t. We know dV dt is equal to 70. So if we could link volume and surface area together, so this is where I think a third rate's going to come in handy. We'll throw radius into it as well. So if I come up with one rate for ds dr, another rate for dV dr, I should be able to link it all together and come up with a formula. And I suppose when you look at the question, it kind of makes sense to tie it together with radius, because they're asking us when the radius is 10. Volume is 4/3 pi r cubed, so dV dr is 4 pi r squared. You may or may not realise it, but there's the link, because 4 pi r squared is, of course, surface area. So dV dr actually equals the surface area. But anyway, let's find the SDR. So the SDR then is 8 pi r. Plug that all in, and we just end up with 140 on r for our rate. So when the radius is 10, we get 14. We're talking about an area, so that would be millimetres squared per second. Millimetres squared per second. Here's an HSC one from a few years ago. Another sphere. Love the spheres. A spherical raindrop of radius r metres. R metres, a raindrop. That's just falling in. Loses water through evaporation at rates depending upon its surface area. The rate of change of volume. Yes, well, if we're talking about metres, one would hope that that's going to be a very small number, isn't it? Because the radius is not going to be metres. So minus 10 to the negative 4 times its area. A, be careful here, with A is the surface area. So T is in seconds, A is surface area. First thing, show that dr dt is a constant. So we're trying to find dr dt. We know dV dt, so ideally we want a link between V and R. So dV dt times dr dV. Let's go work it out. dV dr is 4 pi r squared. Well, 4 pi r squared, that's what I was just saying before, is in fact the surface area. So I'm going to write it as A, because then it'll cancel nicely with the A in our formula. So we'll get 10 minus 10 to the negative 4a times 1 on A. The A's cancel. We get a constant number there. So dr dt is indeed a constant amount, 10 to the negative 4 metres per second. So that was the first part of the question. How long does it take for a raindrop, volume 10 to the negative 6 metres cubed, to completely evaporate? Right, we know dr dt is negative 10 to the negative 4. Now, I've got to find the radius. Not pretty, but there's the radius. So I'm going to have to play with the radius here. I need to know what the radius is. So volume is 4/3 pi r cubed. We know the volume is 10 to the negative 6. So the radius turns out to be the cube root of 3 times 10 to the negative 6 over 4 pi. I'm not going to bother to get a calculation for that. We'll just leave it as an exact value. As I say, scientists are lovely going, oh no, we can't deal with it. That's good enough for us. This is a technique of integration known as separating the variables. What you're basically doing is still just solving an equation. dr dt equals negative t to the negative 4 is an equation. You could think of it as I've done two things in once here. Whatever you do to one side of the equation, you do to the other. Now, you can think of it this way. It's like I've said, I'm going to multiply both sides of this equation by dt. And so I end up with dr equals negative 10 to the negative 4. Whatever I do to one side of the equation, I do to the other. I'm now going to integrate both sides of the equation. But the limits have to be with respect to the relevant thing. So when time was equal to 0, so on my right-hand integral I put 0, the radius was the cube root of 3 times 10 to the negative 6 4 pi. So on the left-hand side, it's the cube root, etc., etc. Up the top I'm saying, hey, I want to find t. I want to find t when the radius would be 0. It's completely evaporated. There is no radius. So I end up with two definite integrals to solve. I mean, there are other ways of doing it. Essentially, I'm saving time and not having to worry about finding the constant of integration. See, I could have said dr dt is negative 10 to the negative 4, so then r equals integrate plus a constant. Then I would have to sub in initial conditions to work out what the constant is. Then I would say, this does it all in one hit. So I like doing it this way, separating the variables, as I say. So t, because if I integrate the t from 0 to t, I'll just get t. Because integrate the t, which is like 1, integrate 1, I'll get t. Substitute t in, minus substitute 0 in. So I know that's going to be t. On the left-hand side, a little bit more work to do. So r, and I'm going to get the cube roots. Oh, you'll notice another thing I did there to save time. Notice how I haven't got negative anymore. And you remember with integration I said you can change the sign if you swap the limits round. So to make it a positive amount, I swap the limits round so the cube root is on the top now and 0 is on the bottom. So we've ended up with 10 to the power of 4 cube root of 3 times 10 to the negative 6 all over 4 pi. Well, to make the scientists happy, let's work it out. It's approximately 62 seconds, that turns out to be. Horrible number, but it is what it is. It is what it is. So, let's play with 7E and 7F, which are rates of change questions. I assume some involve the differentiating, some will involve the integrating.